This is SpaceTime Series 27, Episode 10, for broadcast on the 22nd of January 2024. Coming up on SpaceTime, the Dark Energy Survey. It still can't answer the key question, is dark energy changing over time? Titan's Magic Islands finally explained. And the failed Peregrine lunar lander burns up in the atmosphere above Australia in the South Pacific. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Astronomers taking part in the recent release of data from the Dark Energy Survey say the findings closely follow existing predictions on the properties of dark energy, but still can't answer the key question of whether or not it's changing over time. Dark energy is a mysterious force acting opposite to gravity, causing the expansion of the universe to accelerate over cosmic timescales. The Dark Energy Survey was an international collaboration involving more than 400 astronomers from over 25 institutions. They mapped an area almost an eighth of the entire sky using the 570 megapixel Dark Energy digital camera. The camera was mounted on the Victor M. Blanco telescope at the National Science Foundation's Cerro Tololo Inter-American Observatory in Chile. The survey took data for 758 nights over some 6 years, tracing out the history of cosmic expansion over a wide range of distances with large samples of exploding stars known as Type 1a supernovae. Type 1a supernovae are white dwarf stars that accumulate matter from surrounding material and other stars. When they reach a specific size, roughly 1.4 times the mass of our Sun, they explode in a thermonuclear supernova event. And since they always explode at roughly the same mass, they explode at roughly the same level of luminosity. And consequently, they can be used as standard candles to measure cosmic distances across the universe. It's a bit like looking at a row of streetlights down a road. Even though you know they all have the same intrinsic brightness, the more distant lights will appear fainter than the nearer ones simply because they're further away. And that ratio can be determined using a simple formula known as the inverse square law. And astronomers use this change in apparent brightness to determine cosmic distances. For each supernova, they combine its distance with a measurement of its redshift, that is, how quickly it's moving away from Earth due to the expansion of space-time. Put simply, what the survey has been trying to tell us is whether or not dark energy density has remained constant or changed over time. And that's important because that'll help determine the ultimate fate of the universe. As the universe expands, its matter density goes down. Now, according to the standard cosmological model, the density of dark energy in the universe is supposed to be constant, which means it doesn't dilute as the universe expands. And if this is true, the parameter represented by the letter W should equal -1. But the latest Dark Energy Survey results found that W actually equals -0.80, plus or minus 0.18. Now, combined with preliminary data from the European Space Agency's Planck telescope, W does reach -1 within error bars. So, W is tantalizingly close, but not exactly on -1. If the universe is expanding and the dark energy density remains constant, it means the total proportion of dark energy must be increasing as the volume of the universe increases. The findings, reported in the Astrophysical Journal, covered some 1,499 high redshift Type 1a supernovae using the full 5-year data set of the Dark Energy Survey. So, while the findings are close to what was predicted, they're not a perfect match. That means astronomers will need to develop a more complex model in order to determine if dark energy does indeed vary with time. One of the study's authors, Dr. Annelies Muller from Swinburne University, says the latest findings at least help to reduce uncertainties to new low levels. But she admits more data will be needed.
So the Dark Energy Survey is this international effort that has spanned over a decade. We basically took images from a wonderful telescope in Chile called the Victor M. Blanco telescope, and we imaged the southern sky in certain parts. So we try to understand what's the effect of dark energy in our universe with different probes or different ways of measuring its effect. One of them is using Type 1a supernova, which are these bright exploding stars in faraway galaxies, which allows us to actually measure directly the effect of dark energy. Now, what is the effect of dark energy in the universe? Basically, the universe is expanding in an accelerated way. And we say, to explain this thing that we're measuring, that the reason is that there exists some dark energy that makes this universe expand in an accelerated fashion. Type 1a supernova are amazing objects. So if we want to study how the universe is becoming bigger, you have two choices. Either measure where a galaxy far away is and then wait millions of years to see how much it has moved away, or because we want to do this in our lifetime, we actually use what we call a standard or a standardizable candle. These are objects that shine roughly in the same way. For example, Type 1a supernova, when they explode, we kind of know how bright they are. So basically, if you have a light bulb that has the same power close by or far away, the difference of the brightness that you see here on Earth will be linked to that distance to that object. And Type 1a supernova is exactly that, but astrophysical, very far away, very extreme physics. So it allows us to measure distances to these objects, and together with distances, we measure redshift, which is kind of an equivalence of like a velocity, and with that, we can actually map how the universe is becoming bigger.
That, however, assumes that Type 1a supernovae really are all the same mass, or roughly the same mass, and so really do explode with the same degree of luminosity. How comfortable are you with that?
So Type 1a supernova are standardizable because we think their brightness is powered by nickel 56. So they are not perfect standard candles. They're not all exactly the same, and we know this for a while. They are what we call standardizable. So in the 1990s, we already knew that we needed some corrections on these Type 1a supernova to really get those distances very precisely. So we know, for example, that bluer supernova are brighter, and depending how long they last, you can also correct for that brightness. So we are comfortable with these corrections for the measurements, and we have added during the analysis more and more information. For example, now we know a little bit more about some of the Type 1a supernova. Depending in the galaxies that they live, they are actually slightly brighter or dimmer, and we make these corrections into our analysis. So although they are not perfect, they are still the best probe that we have right now to measure this direct expansion. So I'm pretty comfortable by using them. We have been using them for 25 years, and there is a Nobel Prize involved.
What about things like baryonic acoustic oscillations? Could they be used at all?
Absolutely. So the idea with the dark energy survey is to have different probes to actually check the effect of dark energy in our universe. And what is interesting is like BAO, or the baryonic acoustic oscillations, or the large-scale structure measurements can help us to constrain as well that effect of dark energy in our universe, but in a different way. So each of the measurements that we use, and also weak lensing, for example, tell us something slightly different in a different way. So those results combined is what makes our constraint of dark energy so powerful. So for example, the publication that we released last week that we're very excited about is the tightest constraints on the effect of dark energy in our universe, combining Type 1a supernova from the Dark Energy Survey and measurements from the satellite Planck from 2020. So together, these two gives really, really tight constraints.
And that constraint is W equals minus 0.80 plus or minus 0.18. There's still a bit of leeway there, isn't there?
Yeah, so we can explain what we're measuring with different models. So the canonical model that we use in cosmology is what we call the flat lambda CDM. So lambda is a cosmological constant, something that is not changing with cosmic time, and called dark matter, which is dark matter that is basically not interacting too much. If we use that model to try to explain our observations, we have, as you said, a flat lambda CDM constraint, but we can also try to constrain the data we have with other types of models. And one of the models that we tried, and actually is the almost the preferred one, but barely, is the dark energy that is changing with cosmic time. So through the evolution of the universe, its density is changing. And that could be very exciting if confirmed, because that means that the universe will be slightly younger than we think, and it will give us an idea as well, what could dark energy be? Because for the time being, we don't know whether it's a constant or something changing with cosmic time, and that can actually limit the number of theories that we can use to say what dark energy is.
You'll be making inferences on the teams will be making inferences on the energy density of the universe as a result of all this. In order to maintain a constant, the universe, as it's expanding, has to be getting less dense, but dark energy then has to be getting more dense.
Yes, exactly. So that will be in the case that it's a constant, but it could be the other way around, and we are trying to measure this exactly. For the time being, we're really constraining dark energy between being a constant, what number of that constant, but because we still don't know if it's -1 or -0.99 or -0.95, or whether it's changing with time, with cosmic time, which I think that will be an amazing measurement to have.
The importance of this isn't just to understand our universe as it is now, but also to help determine what the ultimate fate of the universe will be.
Exactly. The more we know about the universe past, the more we can actually extrapolate towards the future. So this is part of what we do. We're kind of historians, but also predictors of how the universe is evolving. So I think it's a pretty cool job.
And right now, I guess the universe looks like it's going to be a cold, dark place. Just our local galaxy group will be visible in the future.
Yes, well, in the very, very, very far away future. So we won't be around to see that one, definitely. For the time being, it will be very slow.
Nothing to worry about.
No, not at all.
The survey, the way you're conducting it, it's grown dramatically. There were only, a small group of stars in the beginning that were isolated and used for the measurements. Now there are almost 1,500.
Yes, it's really amazing. 25 years ago, when all these Type 1a supernovas started to be used to probe the effect of dark energy, there was only around 52 supernovas, okay, Type 1a supernova. And now we have 1,499 Type 1a supernovas that go into these measurements. So it's a huge leap from 25 years ago to now, and a huge effort from a lot of communities around the world trying to get these Type 1a supernova and measure them very precisely. Because when you think about cosmology, we're really trying to get the best measurements that we can.
This takes a lot of observing time to do all this. That must be getting you in trouble with fellow astronomers who want to use the same telescopes for other things. I guess that's where new telescopes like Nancy Grace Roman come in.
Yes, absolutely. So one thing that is interesting is that the Dark Energy Survey took images for 5 years in seasons or parts of the year to get the supernova 1A. Now, we did an analysis, the traditional analysis that we do usually in cosmology, that we classified the supernova with a spectroscopy. So why do we want classification? Because not all supernova are Type 1a. So we only want Type 1a because they are the ones that we can use to measure distance. So if you classify them using the traditional approach, that is using spectroscopy, which is basically having this huge telescope observing this Type 1a supernova and getting their spectra, so basically the decomposition of the light into the different wavelengths, you really only get a small percentage of classification because we don't have enough telescope time to do that. Spectroscopic resources are really, really scarce. And also you need that these supernovas are bright, very bright. And also you need to get that information when they're shining brightly. So this is like a couple of weeks of a time window. So we don't want to take all the telescope in the world. So we changed a little bit how we did this analysis this time. Instead of using a spectroscopy, we use machine learning algorithms to actually select this Type 1a supernova using only the brightness evolution over time that we already had. So we didn't need to take extra information from other telescopes. We could use directly the data from the Dark Energy Survey, and we actually improved that sample by 3 times what we could have with other methods. So I think this is a pretty big thing for us, is that we're really pioneering methods to get more Type 1a supernova from the same data using less resources. And this will be super important for other telescopes like the Rubin or Roman in the future.
So this is looking at the flux at the peak of the light curve using photometry.
Yes, exactly. We basically get the photometry evolution over time. So this we call a light curve, so brightness evolution over time. And with that information alone, we can actually select which are the type 1a supernova, get their probability of being type 1a supernova, and actually use it in our cosmology analysis. And we have shown that this way of doing the selection, that many people didn't believe it was possible, is actually super precise, and the contamination from other objects that from a misclassification is so tiny that it really doesn't affect our results.
And this is where Vera C. Rubin and Nancy Grace Roman come in.
Exactly. So especially I am very involved with the Rubin Observatory because we expect over 10 years to get every night up to 10 million detections of things changing in the sky.
Wow.
And these will include supernova, variable stars, active galactic nuclei, etc., etc., etc. And from these, we really need to get those type 1a supernova for the cosmology. And we expect to get millions of them. But how do we get those millions from this huge data set? And these methods that we're pioneering with the Dark Energy Survey are exactly the answer for that, getting the most out of Rubin in the future.
And the Anglo-Australian telescope has a little role to play as well, I believe.
Yes. So it was really exciting. So we have the Australian Dark Energy Survey that we call AUSTE. Of course, we did a very important job here with the AAT, the Anglo-Australian Telescope. So we use for cosmology, as I told you, distances derived from the supernova, directly from that light curve brightness evolution over time. But to study how the universe is expanding, we also need redshifts. And redshifts, we usually get them from the galaxy that host those type 1a supernovas. So these type 1a supernovae are stars that brightly explode. They live in galaxies. And we actually get a spectra from the galaxy with the AAT to actually get the redshifts that go into our cosmology analysis. So this was a beautiful program that we did over 100 nights in the Siding Spring Observatory. And I can tell you how much I enjoy observing there with the warm bongles around me. It's an amazing place to go.
When you talk about redshift, you're talking about how fast an object is moving away from us.
Exactly.
That tells you how much the universe has expanded or how much space-time has expanded.
Yes, and we need that together with distances to really measure that effect of dark energy. So the two ingredients are important. Getting those type 1a supernova and measuring how they evolve with time, and getting those redshifts to actually understand that expansion. As we grow up in these cosmology measurements, we need more and more information. So the Vera C. Rubin Observatory Legacy Survey of Space and Time will have an spectroscopic counterpart programmed in the foremost telescope that is called TIDES, the program. And that will be the main role of the foremost telescope with Rubin in this time domain astronomy. Roman will be in space, and it's pretty exciting because it's actually reaching wavelengths of light that we cannot get here on Earth easily. So all these three informations will be highly complementary. But we will also have data from DESI, which is a survey getting the large-scale structure in the northern hemisphere. And we will get more and more information as we go through time from different groups of researchers that we can combine all together to constrain the effect of dark energy in our universe. So it's a huge collaborative effort, and it's very, very international.
Based on what you know so far, what can you tell us about dark energy?
So dark energy we have confirmed that dark energy is actually there. Our observations can only be explained with the presence of dark energy. This is one of the most important parts. And the second part, and I think that's like the tantalizing hint that we have, that dark energy may not be the constant that for 20 years we have thought it is, but maybe is something that is varying with cosmic time. And I think that's really, really exciting. However, we need to wait for Rubin and Roman to be online, taking data and do this analysis to actually confirm this. So the truth is, for the time being, we don't know what dark energy is, but the more we measure its effect on the universe, the more we will be able to say, oh, it cannot be this, it cannot be that, it cannot be that, then it must be this, and then try to get more measurements to confirm it. So slowly we're peeling that knowledge from the universe.
What about the idea that what's happening here is more dependent on our position in the universe? For example, the readings would be different if we're located in a large void rather than in the middle of a filament in the cosmic web.
Yes, so there's a lot of people trying to probe this. For the time being, we haven't found any evidence that the universe looks different from one place to the other. So we have the cosmological principle where for us the universe is the same wherever you are.
It looks the same the same in all directions.
Yeah, basically. You can have some local changes. For example, we live in a galaxy group. There are some velocities from this local group. So if you measure things close by, you need actually to correct for this. But this is very local. This is not in the large scale of things. So in the large scale of things, looks all the same.
Okay, so the void doesn't come into it then.
Until now we haven't found any evidence that that's the case.
An important role in all this is that played by artificial intelligence and machine learning. Tell me about it.
Yes, it's very exciting because these are very new technologies that we're seeing their effect in our society. We have all heard about ChatGPT and all these machine learning recommendation systems that we have nowadays in our day-to-day life. But how can we use this technology to do science and to really harness the power of these huge data sets that we make so much effort in getting? And this is exactly what we did. We took data from the Dark Energy Survey. We developed a classification algorithm using machine learning. So I developed the main one using deep learning algorithms. And we were able to use this technology to really, really precisely classify this type 1A supernova. So it's pretty amazing that this technology can be in our day-to-day, but can also be in these high-precision measurements of how the universe is becoming bigger. So when you think about it, it's a little bit mind-blowing, no?
One of the big scary things about artificial intelligence is that it's a black box. We often don't understand how it reaches its conclusions. That's got to be especially concerning for science.
Yes. So a big part of my research is interpretability. So understanding how the machine learning algorithms classify objects and how robust this is. So we did a lot of tests trying to break the classifier and the machine learning algorithms to see if we were doing something that affected the cosmological results that we would get. And we tried for many years, not only myself, but other groups in the UK and in the US, and we couldn't break it. So we were really, really careful trying to get this machine learning algorithm in a way that is not only a black box, but it's something that is robust and you can trust its outputs. But of course, if you're curious about becoming not a black box in machine learning, there are so many things that we are doing right now to try to open the knowledge on what the machine learning algorithm is paying attention on, or how confident it is. Would you give it, for example, for training dogs and cats, and you give it an image of a zebra, and you ask it what it is. So these are all studies that we're actually doing not only because we are curious, but also because for us it's important in cosmology to be sure that the output makes sense.
That's Dr. Anais Muller from Swinburne University in Melbourne. And this is SpaceTime. Still to come, Titan's magic islands finally explained, and the failed Peregrine lunar lander finally ends its mission, burning up in the atmosphere above Australia in the South Pacific. All that and more still to come on SpaceTime. Saturn's largest moon, Titan, is the only world in our solar system other than Earth where clouds form liquid rain, which then pours into rivers and flows into lakes and seas. But on Titan, the liquid isn't water, it's ethane and methane. On Titan, it's so cold, the water's frozen solid, forming part of the bedrock. Now a new study claims ethane and methane and other organic compounds on Titan can accumulate on the surface as chunks. And they may even be carving off like glaciers at the edges of the Saturnian moon's methane lakes, forming the ephemeral magic islands. Astronomers have long wondered about these magic islands, which appear in some images and then disappear. And they don't always appear at the same spots, but seem to float across the lake's surface. It's all incredibly mysterious. The findings, reported in the journal Geophysical Research Letters, describe how Titan's magic islands are likely to be floating icebergs, chunks of porous frozen organic solids. A hazy orange atmosphere, 50% thicker than Earth's and rich in methane and other carbon-based or organic molecules, blankets Titan. When the European Space Agency's Huygens lander descended from NASA's Cassini mission down to the surface of Titan, it touched down in what it later described as feeling like wet sand. But the strangest thing were the Cassini radar images of shifting bright spots on the sea's surface of Titan, which appear to last from just a few hours to several weeks or longer. Scientists first spotted these ephemeral magic islands back in 2014 with the Cassini-Huygens mission and have been trying to work out exactly what they are ever since. Previous studies suggested they could be phantom islands caused by waves, or real islands made of suspended solids, floating solids, or simply bubbles of nitrogen gas. The new study's lead author, Jingting Yu from the University of Texas in San Antonio, wanted to investigate whether the magic islands could actually be organics floating on the surface, like pumice from volcanic eruptions floating on water here on Earth. Titan's upper atmosphere is dense, with diverse organic molecules. These molecules can clump together, they can freeze, and they can fall down onto the moon's surface. And that includes falling onto eerily smooth rivers and lakes of liquid methane and ethane, which have waves only a few millimetres high. Yu and her colleagues were interested in the fate of these organic clumps once they reached Titan's hydrocarbon lakes. She wanted to know whether they would float or sink. To find an answer, the team first investigated whether Titan's organic solids would simply dissolve in the moon's methane lakes. Because these lakes are already saturated with organic particles, they determined that the falling solids wouldn't dissolve when they reached the liquid. The thing is, Titan's lakes and seas are primarily methane and ethane, both of which have low surface tension. That makes it harder for solids to float. The model suggested that most of the frozen solids would have been too dense and the surface tension too low to create Titan's magic islands, unless, that is, the clumps were porous like Swiss cheese. If these icy clumps were large enough and had the right ratio of holes and narrow voids to solids, then the liquid methane would only seep in slowly, possibly slowly enough for the clumps to linger on the surface for a while before becoming saturated and sinking. The author's modelling suggests that individual clumps are likely too small to float by themselves. But if enough clumps are massed together near the shoreline, larger pieces could break off and float away, similar to how glaciers carve off on Earth. So, with a combination of a bigger size and the right porosity, these organic icebergs could well explain the magic island phenomena. And in addition to the magic islands, a thin layer of frozen solids coating Titan's seas and lakes would also explain the liquid body's unusual smoothness. And so, these findings could explain two of Titan's many mysteries. This is SpaceTime. Still to come, the Peregrine lunar lander breaks up in the skies above Australia and the South Pacific. And later in the science report, Chinese scientists say they've been experimenting with a new mutant strain of COVID-19 that is guaranteed 100% lethal. All that and more still to come on SpaceTime. Mission managers have now confirmed that the troubled Peregrine lunar lander made a fiery return to Earth on Thursday, burning up in the skies over eastern Australia and the South Pacific during atmospheric re-entry. The 1,283-kilogram spacecraft had been launched 10 days earlier as the primary payload aboard the maiden flight of the United Launch Alliance's new Vulcan Centaur rocket. Included aboard the lander were a series of NASA experiments, as well as the partial remains of at least 70 people and a dog as part of a space burial promotion. While the launch of the Vulcan Centaur and payload deployment went smoothly, the Peregrine lander began experiencing problems soon afterwards. Peregrine's operators Astrobotics say technical anomalies began when Peregrine failed to orient its top solar panel array towards the sun in order to charge its batteries. At the same time, it was drifting off course, and then suddenly communications were temporarily lost. Eventually, engineers were able to re-establish contact and reorient the spacecraft to keep it tilted in the right direction to keep its solar panels pointing towards the sun. The problem was eventually traced to a faulty valve in part of the spacecraft's propulsion system. An image taken by an onboard camera showed the multi-layer insulation badly damaged by what appears to have been some sort of propulsion system explosion, resulting in a dramatic loss of fuel and, in the process, dooming the mission to fail. It means Peregrine would never have had enough fuel to make a soft landing on the moon. While Peregrine could have been commanded to crash onto the lunar surface or left drifting in space, Astrobotic instead elected to return the probe to Earth, so it could burn up in the atmosphere and prevent it from adding to the growing problem of space junk. While the Peregrine mission is now over for Astrobotic, all is not lost. Astrobotic have another chance to reach the moon in November, when their Griffin spacecraft lander, transporting NASA's Viper lunar rover, will attempt its own landing on the lunar surface at the South Pole. We'll keep you informed. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Ice sheets around the world have been retreating over the last few decades, but a new study shows that the Greenland ice sheets have been shrinking at an especially fast rate since the 1990s. The findings, reported in the journal Nature, are based on new satellite observations showing that Greenland has lost more than 1,000 gigatons of ice since 1985. The new observations show the extent of this retreat. They find that Greenland has lost about 5,091 square kilometres of ice cover just in the last 4 decades. In fact, the analysis shows the ice sheet shrank by an average of 218 square kilometres every year since January 2000. The authors say this loss doesn't appear to substantially contribute to sea level rise because the ice is already floating on the water, but it may be playing a critical part in ocean circulation patterns, and consequently how heat energy is distributed across the planet. Well, just 4 years after the start of the COVID-19 pandemic in Wuhan, China, Chinese scientists have confirmed that they're experimenting with a new mutant strain of COVID-19 that has proven itself to be 100% lethal in humanized mice. The deadly new virus, known as GXP2V, attacks the brain after first infecting the lungs, bones, eyes and trachea, with victims dying within 8 days. A report on the preprint website BioArchive states that in the days before their deaths, victims lost a lot of weight, exhibited a hunched posture, and moved extremely sluggishly, with their eyes turning completely white on the day before death. An ex-post by Professor Francois Ballou, an epidemiology expert at the University College London's Genetics Institute, slammed the research, describing it as terrible and scientifically totally pointless. Others say it could be a new biological weapon. Official figures suggest over 7 million people have already been killed by the COVID-19 coronavirus since it was first detected among workers at China's Wuhan Institute of Virology back in September 2019. However, the World Health Organization estimates the true death toll is likely to be above 18 million, with some 775 million confirmed cases globally. Scientists have successfully cloned a healthy rhesus monkey which has now survived more than 2 years. While cloning has become more and more common with plants and lower-level animals, cloning primates has been especially difficult. Now, a report in the journal Nature Communications claims the key to success with primates involves providing a cloned embryo with a healthy placenta. The authors analysed the differences between 2 early-stage embryos made from 2 reproductive technologies, those using in vitro fertilisation and those cloned using a process called somatic cell nuclear transfer. They found abnormalities in the way genetic information can be assessed and read by the developing cloned embryo and in the size and shape of the placentas enclosed monkeys developing in surrogate mothers. To address these issues, researchers have now developed a method to provide the developing cloned embryo with a healthy placenta, in the process successfully developing a healthy cloned monkey. A new study suggests that narcissists are far more likely to believe in conspiracy theories than the rest of the population. The findings are based on new research looking at the different characteristics and personality traits associated with belief in conspiracy theories. Scientists found a consistent link between conspiracy beliefs and narcissism, especially conspiracy theories supporting a person's belief system or worldview. Tim Mendham from Australian Skeptics says buying into conspiracies makes some people feel like they have special knowledge, which when you think about it is incredibly alluring to any narcissist.
This research by a PhD student at Bond University in Queensland was trying to see the motivations for people to believe in conspiracy theories, why they picked up on this one, not that one, etc., and whatever. And they were suggesting that one characteristic of some conspiracy theory believers is narcissism, their own belief in themselves and the wonderfulness that they are. He was suggesting, this researcher, that following a conspiracy theory makes you feel special, right? That I've got this knowledge that others don't have, therefore I'm pretty cool. And that you don't have it, you're stupid, I'm bright, and therefore I will believe a conspiracy theory because I believe in how important I am and my judgment is. Now, one thing the researcher doesn't say, but you could add, is also that definitely narcissistic, that a conspiracy theory is they're after me because I'm important, I have this special knowledge, etc. So that's very narcissistic. It ends up being paranoid as well.
Just described my friend George to a T.
And I describe people I know too, who say, they're after me, they will try and kill me. And I once said, you're not that important that people would want to kill you.
I use that argument with George and he totally dismisses it.
Because he's narcissistic. But what this researcher was saying is that people who have a high opinion of themselves, whether it's the Dunning-Kruger high opinion of themselves, or they're really not worthy of it, they have a high opinion of themselves and that therefore they can see things that others can't. And why can't they see it? It's so obvious to me because I'm super bright and so observant. And at the same time, I'm so important, I can see this stuff and that they will come and kill me because they have this secret knowledge and because I'm important. And therefore the narcissism works into paranoia and all sorts of things, but it's definitely about the belief that they have special skills that others don't. Now, not every believer in a conspiracy theory is going to be a narcissist, and not every narcissist is going to believe every conspiracy theory, but it makes for an interesting concept because you can't tell narcissistic people that that's what they are, and they have a firm commitment to the conspiracy theory that they follow, so you can't necessarily weed them off. But that's true of anybody, whether they're narcissistic or not. But narcissists will take a correction as a personal attack.
Yeah, when my friend George raises this issue and I challenge him on it.
Why are you going after me? I'm brighter than you, therefore I have special knowledge, and you don't.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to SpaceTimeWithStuartGary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.